Grégoire.
Hi. Can you hear me? No. Thank you. Hi. So, this will be more practical talks. I will present you an algorithm for type checking and marshalling values. So, just to be clear, marshalling is a process, is a convention between the runtime representation of a data and a sequence of bytes that one may externalize, for example, to be sent through the network and marshaled in another process. Okay, and hopefully, unmarshalling is the reverse operation that reallocates the data in the heap. Okay, usually we can distinguish between two kinds of implementation. The first one is based on a set of ad hoc unmarshalling primitives for each data types, and such function can be written manually. This is painful, or it could be generative, as shown, for example, by Kennedy in the functional curves in 2004. And the second approach is to only have one pair of generic marshalling and marshalling primitive that is not written in the host language but provided by the runtime. And for example, those two, the Java method or the OCaml function. And the question I want to address today is how to ensure type safety in the second kind of unmarshalling primitive. Once again, we can distinguish two situations. The first one, when the semantics of the language require to keep type information in the runtime. So, like in Java, for example, we just have to serialize the type together with the value, and the unmarshal function could use those type information to type check the value. And the second point is the one I will specifically talk today, is when there is no type information in the runtime representation of data. And we have no other source than to fully explore the graph to check the compatibility of the data. So I will briefly present the data types we want to be able to marshal and unmarshal. Then I will present the algorithm with four specific situations we have to handle, and I will just say a word about the formalization we described in the paper at the end. So our host language, our test bed was the OCaml compiler. So we want to be able to marshal algebraic data types, including generalized algebraic data types. We want to be able to serialize mutable data, and also closure if possible. And we choose OCaml because this is a runtime representation with very few type information. We are just able to distinguish between immediate value, integers, and allocated blocks. So here this is the initial ID, the simple ID. Here we have a list of rational number, and if we just want to work through the value and propagate the expected types together. So for example, here if we want to check that this memory graph corresponds to a list, we have to check that there exists that a block of size 2 with the tag 1 correspond to a case in the type definition. Here it corresponds to the third constructor, and given this type information, we can get the expected type for the third value and recurse. Okay. The first if we want to be able to unmarshal mutable data, we have to ensure that we do not type check a shared block with multiple different types that are incompatible. So we have to traverse the graph in a topological order. This will allow us to collect all the expected type for a shovel block. In this example, we will collect a tree of car and tree of int for the lift. And at these steps, we will compute the principal anti-unifier of all the collected types. In this case, for all alpha, tree of alpha. And if the shovel block is compatible with this anti-unifier, it will be compatible with all the expected type. And this is obviously complete also. And this approach is sufficient to handle also cycle in the memory graph. We will traverse, the topological sort will, we will traverse the graph, strongly connected components one by one. And when we found backward reference, we have two situations. If the new expected type is an instance of the first all the external expected types, it's okay. If it's not an instance, we can, like in the second example, where we have nested data types, where we may once again anti-unify the new expected type with the first expected type and recurse. And this process terminates because each anti-unification step decreases the size of the type. Third step in the algorithm, we want to be able to unmarshal value belonging to a GADT. And this is the same process that ADT, classical ADT. We just have to add one unification steps to check that the expected type is compatible with the origin type of the corresponding type constructors. And this unification step will also allow to instantiate some existential types introduced by GADT. For example, in the last case of this type, which is named first, the beta variable could not be instantiated by the expected type. If we had, this variable will be instantiated when we check if there is a type beta, such as car of A is compatible with beta, the T of beta. The introduction of non-instantiated type variable will change the order of traversal, because we are not able to check a value when the expected type is a non-instantiated variable. So in this example, we have to, for the DIN value, we have first to check the second value to instantiate the type variable into int, before to check that 65 is compatible with int. And luckily, all the mechanism we introduced for ending GADT could be used to type check closure, provided we are able to marshal and unmarshal closure, meaning we are able to rebind the coin pointer, and provided we are able to associate to each coin pointer its static type and the corresponding typing environment. Here, once again, we will not be able to, it's only when we will unify the type of the second closure that we will know that 52 should be an int. We expect that 52 should be an int. Just to conclude with closure, there is some situation where we are not able to recover the type for non-instantiated type variable, and here the length is a polymorphic function, and we have no type information about the element of the list. But as shown by Goldberg and Blogger in '92, if we are not able to reconstruct the type, we have parametric CT results, and all those values are not useful, and we can safely ignore them. Maybe even not unmarshal them. And last part and maybe the most critical one in the algorithm. If we want to be able to handle GADT in the presence of sharing in the memory graph. Suppose we have collected those three types for a shared block. We are not able to anti-unify all those types because the anti-unifier depends on the further instantiation of the type variable. However, if we want this anti-unifier not to be trivial, all the types should share the same head-type constructors. Otherwise, the anti-unifier will be for all alpha.alpha, which is the empty types. And so here we can introduce two new variables, gamma 1 and gamma 2, and then instantiate gamma 1 maps to gamma 2. Okay, still with this refinement, we are not able to anti-unify those types. So we have to generalize a little bit our algorithm, and instead of taking a graph on a type, we will take a graph on a set of types and state that our algorithm will succeed only if the graph is compatible with all the types, and more precisely with the anti-unifier of all the types. And we have to ensure that we keep this property all the time. And okay, so if the algorithm expect a set of types, we can decompose all the expected types and recurse on the sub-value with the set of all the set of expected type. And we have a small lambda showing that this is sufficient to be complete in presence of sharing. But in presence of cycle, if while checking a strongly connected component, we introduce new type variables, and the set of expected type for the roots of the strong component may increase indefinitely, and we have no, in the general case, we have no termination arguments. Okay. So, before to conclude, I just want to say a word about the formalization, how we formalize this graph traversal algorithm. So we use a rewriting system for which the terms are basically a set of constraints. The constraints representing the block remaining to be checked, and okay, so it's a conjunction of constraints. Basically, it's a conjunction of constraints, and you can see there is all the elements presented before. We have existential quantification for the non-instantiated variable and the corresponding unification, and we have the last one is predicate to ensure that a set of types share the same type constructors. Okay, and to prove the soundness and completeness of our algorithm, we define first a type system for the memory graph, associating a type to each pointer, and we prove the soundness, meaning if the initial constraint revives to true, then the memory graph is compatible, and the semi-completeness, if the initial constraint revives to false, the memory graph is not compatible with the expected types. And we prove also that the two normal forms of our algorithm is true and false. And as said previously, we prove the termination in two situations: in the presence of cycle, but the absence of a non-instantiated type variable, and obviously also in the absence of cycle. In our prototype, we ensure the termination by limiting by bounding the number of times we check a strongly connected component without decreasing arguments. Okay, and so to conclude, I present you an algorithm for checking the type compatibility of a memory graph, an unmarshalling memory graph that is correct on semi-complete, and the use of a rewriting system has proved useful for many reasons. It is a proof of soundness and semi-completeness because we have to prove each rewriting rule independently. The semi-completeness, we just have to prove that every rewriting rule preserves the satisfiability of a constraint. For the soundness, it's the contrary. And the use of rewriting system also allow to describe rewriting strategy to describe efficient graph traversal independently of the correction properties, and it also helps to define, to add new rewriting rules that are just correct, but allow us to obtain the termination in the most general case. And thank you.